We have mapped the rocky terrain of our inner neighbors, Mercury, Venus, and Mars. But for centuries, the gas giants at the edge of our solar system remained out of reach, appearing as faint, unresolvable points in the dark. Reaching these worlds required crossing a physical barrier 160 million kilometers beyond Earth's orbit. This is the asteroid belt, a 160 million kilometer wide graveyard of rock and debris left formation of our solar system. In 1972, scientists estimated a 1 in 10 chance that spacecraft entering the belt would suffer a collision. But when Pioneer 10 emerged unscathed 7 months later, it proved the rocks were spread across such an enormous volume of space, making navigation possible. This breakthrough allowed NASA to exploit a rare planetary alignment occurring only once every 176 years. By launching the twin Voyager probes in 1977, engineers could harness the gravity of each outer planet to swing the craft from one world to the next using minimal fuel. These machines were designed to survive the vacuum of space for decades, yet they were powered by hardware we would now consider primitive. Their onboard computers used old television studio cameras and recorded their data on 8-track tape. By launching these probes, humanity began an outward push that replaced distant speculation with a detailed physical record of the outer planets. When the Voyagers reached Jupiter, they revealed a planet dominated by complex weather patterns. The most prominent feature was the Great Red Spot, a shrinking, high-pressure cyclone that has been observed for nearly 4 centuries. To understand the scale of these storms, consider that the entire Earth could fit inside the Great Red Spot with room to spare. Jupiter's immense gravity makes it the solar system's dominant force after the Sun. It acts as a gravitational bully, pulling in rogue space debris. We saw this in 1994, when the comet Shoemaker-Levy 9 was torn apart by the planet's gravity, with its fragments releasing more energy than Earth's entire nuclear arsenal upon impact. This gravitational influence also affects Jupiter's moons. The constant tug of the planet creates rocky tides that turn the moon Io into a volcanic hellscape, while providing enough internal heat to maintain a vast, circulating liquid subsurface ocean on the icy moon Europa. Decades later, the Cassini-Huygens mission arrived at Saturn to investigate its natural satellites and its iconic ring system. By performing dangerous dives through the rings, the spacecraft discovered that they are not static. They are actively raining ice and rock onto the planet's surface. On Titan, Cassini found a world where organic molecules like methane and ethane rain from the clouds and flow into vast lakes. Meanwhile, on the tiny moon Enceladus, saltwater geysers erupt from a buried ocean, carrying the chemistry necessary for life into space. These discoveries confirmed that the moons of the gas giants are dynamic environments, featuring liquid water, energy sources, and complex organic molecules. This makes them our most promising candidates in the search for extraterrestrial life. Voyager 2 continued billions of miles further into the freezing domain of the ice giants. In this region, the Sun is so distant that it provides almost no heat to the planets it orbits. Uranus is a planetary oddity. Likely knocked onto its side by an ancient collision, the planet sits at a 98-degree angle, with atmospheric temperatures plunging to minus 224 degrees Celsius. Neptune proved equally extreme, featuring an atmosphere with winds reaching 2,000 kilometers per hour, the fastest in the solar system, and a dark, Earth-sized hurricane raging in its southern hemisphere. Before these encounters, the outer planets were assumed to be uniform gas balls. Voyager 2 proved the ice giants were distinct, violent worlds that followed their own rules. In 2006, the New Horizons probe launched to explore the region beyond our outermost planet. Its mission was to conduct the first encounter with the dwarf planet Pluto. The images returned were a revelation, showing a geologically young nitrogen ice heart and a naturally blue sky, features that were entirely unexpected at a distance of 5 billion kilometers from the Sun. Pluto is just one object within the Kuiper Belt, a vast ring of icy remnants left over from the earliest days of our solar system's formation. Observations of this region reveal a mathematical anomaly. Most Kuiper Belt objects follow standard symmetrical orbits, but distant rocks are pulled off target. These orbits all line up in one direction, hinting at a massive super-Earth dubbed Planet 9. Mathematical models suggest it is roughly the size of Neptune, hidden from our telescopes by the dense star fields of the Milky Way. Reaching the edge of the known map has not provided a final answer. Instead, it has uncovered a new mystery that suggests our solar system is larger than we ever imagined. Both Voyager probes have now crossed the heliosphere, the boundary where the sun's physical influence ends, and are currently traveling through true interstellar space. Maintaining contact from billions of miles away requires the Deep Space Network, a global system of massive communication dishes that can capture the weak radio signals sent back from the edge of the dark. In 1990, Voyager 1 turned its cameras back toward the inner solar system to capture a final panorama, a family portrait of the planets we left behind. Within a single beam of sunlight sat a tiny pale blue dot. The image showed Earth as a fragile speck suspended in the vastness of space, providing a permanent reminder of our place in the universe. In 50 years, these robotic emissaries have mapped the once distant giants, turning points of light into a physical catalog of worlds that continue to beckon us outward.